Hi guys. In this video, we are going to take a look at chapter 2. In the previous chapter, we looked at Anton van Leeuwenhoek and how he was the father of microbiology because he invented the first microscope. Now, one of those early microscopes only had one lens in it. So it was really kind of not very advanced. So in this chapter, we're going to take a look at that very instrument and some of the other early, instruments as they kind of progressed. And now we're going to take a look at what we're used today in our laboratories and how we view the microbial world. So let's take a look at that. So let me share my screen with you guys and let's take a look at just that. So viewing the microbial world here, we're looking at chapter 2. So in this chapter, we're going to take a look at using the metric system. If you guys remember from math, we did use the metric system. I'm not going to have you doing a whole lot of conversions today. Don't worry about that. I'm going to show you a little bit of math and I'll explain, and it's going to be very, very, very basic math. But we use the metric system to express sizes of microbes, and I'm going to explain that. And then we'll take a look at these microscopes. We'll take a look at some of those early microscopes. Remember, Anton van Leeuwenhoek invented what was called a simple microscope because it only had one lens in it. And I'll talk to you about that. And today we're going to see the most common microscopes that we see in our labs today. We have them at ATA. We see them typically in most laboratories are what's called a compound microscope. And then even more advanced than that, in some, again, more advanced laboratories, you guys are going to see what's called electron microscopes. And I'll talk to you guys about what those are. So let's take a look. So we just mentioned that we use metric sizing to express sizes of our microbes. Remember when we talked about metrics in math, that remember metrics were, depending on what you were measuring, you either used grams, liters, or meters. Grams were used to measure the weight of something, so how heavy something was. So that's why when we measure patient body weight, we use kilograms, not kiloliters, right? It's kilograms because we're measuring their weight. So again, grams are used for weight. Liters are used for liquid. So if I was measuring how much is in my cup here, I would use probably liters or milliliters, right? Milliliters is liquid measurements. Whereas then meters was used to measure a length or a distance. So like centimeters, something we're probably more familiar with. Meters, the end of that word there, is again used to express length. So that's what we're going to focus on here today, is again that meter measurement. So the basic unit of length in the metric system, as we're looking at that second bullet point there, and as I just mentioned, is called the meter. It is equivalent to about 39.4 inches. It's very similar to about a yard. For those of you guys familiar with the measurement of a yard, if you guys have ever seen a yardstick, that's literally 3 feet, which is about 36 inches. So again, a little bit longer than a yard, but very, very similar. 39 inches, we're not too far off here. So again, just kind of picturing that length of that meter there. But again, we're going to go even smaller because remember, you cannot see microorganisms with the naked eye. That prefix micro there is kind of a clear indicator that that's where we're going to look at there. So when we talk about bacteria and viruses, our most common microorganisms today, that's what we're going to compare. So let's take a look. So the sizes of bacteria and protozoa, which again we won't worry too much about, are usually expressed in terms of micrometers. So that in math, again, we typically stayed away from this little symbol here that looks kind of like a U. In math, there was a big reason why we did that when we, instead of using that for micro, because it sometimes looks like an M and it can be confused with milli. So depending on how quickly you write it, so we typically use MC to abbreviate micro. So if you see MC, that's what that is. But that's what that little symbol indicates there, is micro. So a micrometer, just so you guys, if you guys, just want to go back to math for a second, when we talked about this in your all's math class, again, whether you had me or somebody else, hopefully this was covered for you guys. But again, a meter, again, picture about a yardstick, cut that into 1,000,000 pieces. If we were to cut that into 1,000,000 little pieces, one of those tiny little pieces is a micrometer because it is 1/1,000,000th of that meter. Okay, so that's what that means there. A micrometer is 1/1 millionth of a meter. So imagine how very, very tiny that is. Probably, again, not something we'd be able to see with the naked eye. So that's how we measure bacteria, whereas viruses are going to be a little bit different. So just to kind of show you guys your typical average sizes of your bacteria, a typical spherical bacterium, which is called a coccus. If you look at multiple what they're called coccus, if you look at multiple of them, it's called cocci. We'll talk about this when we cover bacteria in chapter 4. But a typical, again, your average spherical shaped bacterium is about 1 micrometer in diameter. So just kind of giving the idea about how big that is. We also have what's called rod-shaped bacterium, which means they're just a little bit longer than they are wide. They're called bacilli. It's about 1 micrometer wide, so the same width as your cocci, by 3 micrometers long. So again, not very big at all. Okay, we're talking about micrometers here, so very, very, very small, and we're going to need to use a microscope in order to see this. So this gives you that visual I was giving you guys, or trying to show you guys that, again, a meter, very similar to the length of a yard. It's 39.4 inches. So again, about this gentleman's arm span here. So again, if we were to take that and cut it into 100 pieces, one of those would be a centimeter. If we instead cut it into 1,000 pieces, one of those would be a millimeter. Most of your rulers have centimeter and millimeter markings on those, and they're easy to see. But today we're going to focus on these last two. I know in math, we really stopped at micro. We didn't go any further than that. And I'm going to show you guys what that last one means. But again, if we cut this into 1 million pieces, one of those tiny little pieces would be a micrometer. Now let's go even further than that. So we actually have a smaller unit than micro. If we were to actually cut this meter into now 1 billion pieces, so a little bit different than million, again, a whole lot more pieces there. So much, much smaller measurement is what we're talking about here. If we cut that into 1 billion pieces, 1 billionth of a meter is now called a nanometer. So that prefix nano means 1 billionth. That's why you see all those little zeros there. 9 zeros is a billion. So just to show you guys that the reason why I bring up nanometers is because viruses are significantly smaller than bacteria, and we're going to use nano to express the measurement of our viruses. So that's what we bring up here on our next slide. The sizes of viruses are expressed in terms of nanometers. Again, a nanometer is equal to 1 billionth of a meter. So we're seeing, again, whole lot smaller. Most of those viruses that cause human diseases are going to range anywhere from 10 nanometers to about 300 nanometers. So I know you guys look at those numbers 10 and 300 and think, well, a bacterium was only 1 micrometer. But 1 micrometer is significantly larger than 10 nanometers. Nanometers, again, being such a smaller measurement. Again, it's like saying that, the length of, this notebook is 12 inches. Let's call it 12 inches. But if, again, we're measuring in a different length, 12 inches is the same thing as 1 foot. Okay, so it's just kind of comparing the two. A foot, we know that measurement is a lot bigger than an inch, right? So again, even though the number itself seems bigger, the measurement itself and that unit being expressed is so much smaller. So nanometers are significantly smaller there. The exception, as far as our viruses are concerned, the exception is going to be the Ebola virus. If you guys are familiar with that Ebola virus, it can cause viral hemorrhagic fever. Those are actually a little bit bigger than your average virus. They can be as long as 1,000 nanometers, which is equivalent to 1 micrometer. So it's about the same size as your average cocci, so your coccus bacteria. Again, we talked about in the bacteria there. So, but to compare the two, if we are looking on average, bacteria compared to viruses are significantly smaller than bacteria. So just FYI, when using a microscope, like I said, we can't see any of these measurements with the naked eye. We need help. We need a microscope. So we look through the lens of a microscope and we're able to view these organisms. When we measure them, there is a particular instrument that helps us with that while using the microscope. and that helps us to measure the sizes of these microorganisms, and that is called an ocular micrometer. So ocular, when you see ocular, it's typically meaning that you're using your eyes, like an eyepiece of some sort. And then the micrometer, we're familiar with that. We just talked about micrometers. So that's the name of the instrument that's being used to help us measure these microorganisms. Okay. So just as again, a refresher, so just to give you guys an idea and try to give you guys again more of a visual of just how small these organisms are. Again, bacteria are expressed in units of micrometers. So if we were to take 7 cocci, remember we talked about a couple slides ago that your coccus is just your average spherical shaped bacteria. If we were to take 7 of those guys, they could fit into 1 red blood cell. So something else we cannot see with the naked eye. When we can see blood when it comes out of our skin, but you can't look at that blood and see 1 red blood cell. So again, something else we would need a microscope to help with. But to show you how much smaller they are than those cells, 7 of those are the same size as that 1 red blood cell. Even kind of more of a measurement here. If the head of a pin, so like a push pin, if at the head of a pin, let's say it was 1 millimeter in diameter. Now that's something we would be able to see with the naked eye. We can see 1 millimeter. It's still really, really, really small, but we can still see it. But if we're looking at that and we're saying it's 1 millimeter, then 1,000 of those cocci could be placed side by side, lined up together on the head of that pin. 1,000. That shows you just how much smaller that is than your millimeter there. So that shows you how small your bacteria are. But even smaller than that, viruses. Viruses, again, expressed in units of nanometers. Once again, they are about 10 to 300 nanometers in length. It does give you the figure here. I don't even have my book with me, I don't think. Yes, I do. It does say that it's on page 14. I actually just kind of FYI have an older version of your all's textbook. So it may be a different page number. If it is, it's around that same page number. It may be 15 or something like that. Let me see if it's 14 in my book. Just real quickly here. Yeah, for me, I'm looking at, just to show you guys on my book here. And for those of you guys who may not have a book, you guys can see what I'm talking about. Let me show you just the comparison here. So this picture that's in your textbook shows you, here's a cocci, so a coccus, I'm sorry, talking about singular there. This is your average bacteria shape. We're looking specifically at Staphylococcus. We'll talk about those prefixes and what those different terms mean. But that's showing you that size of that average bacterial shape compared to these different viruses over here. This is the herpes virus. This is the pox virus, chlamydia, polio virus, really, really small, and the influenza virus. So the reason that it shows those pictures is to show you can see in the comparison here that viruses are significantly smaller than your bacteria. Okay, so just FYI on that. So I just wanted to show you guys that. All right, let's go back to where we were then. Okay. All right, so microscopes. Microscopes, again, just talking about, how we view things. If we think about, how we view the world, we obviously view through our eyes, right? So the human eye, as well as a telescope, a pair of binoculars, a magnifying glass. For those of you guys familiar with a magnifying glass, it's just a lens you can hold up in front of a newspaper or something so you can make the words look a little bit bigger. Sometimes people who have trouble seeing things and reading things use a magnifying glass to help amplify the sizes of those words. So a magnifying glass and a microscope itself, these are all various types of what's called an optical instrument. Optical, it allows us to view. Eyeglasses would fall into this for those of you guys who wear eyeglasses, because it's a type of instrument that helps us to view the world. And again, your eyeballs count as that. But a microscope is an optical instrument that is going to be used to observe very tiny objects, objects that are so small that they cannot be seen with the unaided human eye. So each optical instrument, so all those that we mentioned, they all have a limit to how big it's going to make what we're trying to view. It has a limit as to what can be seen with that instrument. This limit is referred to as what's called the resolving power, or sometimes called the resolution of that instrument. If we're thinking about that, remember, human eye, I can only see so far. I can only see something so small. But I may need a magnifying glass to then make that a little bit bigger. And it has a limit too. I wouldn't be able to see a virus or bacteria with a magnifying glass. I can see small print in a book. I might be able to help to see that a little bit better. It's going to magnify it a little bit, but it has a limit. It only has a certain resolving power. But then a microscope goes even further. So it helps me even more. So that's what I mean by that. So the resolving power, just FYI, of an unaided human eye is approximately 0.2 millimeters. That's the smallest object most individuals can see with the unaided eye, meaning without eyeglasses, without a magnifying glass, and without a microscope. That's the smallest. And again, that varies obviously from person to person, depending on the individual's vision. But on average, it's about 0.2 millimeters. That's our limit. That's how far we would be able to see, or how small we'd be able to see. So here are some of your early microscopes, those earliest known microscopes. So Anton van Leeuwenhoek's microscope is in here. Again, when he invented that instrument, people came after him and said, I'm going to try to make that better. And we've seen many different microscopes since then, as that time has progressed. He invented, again, what was called a simple microscope. It's called a simple microscope because it only contains one magnifying lens. In fact, a magnifying glass itself, what I was mentioning to you guys earlier, the lens that you can hold to help read small, fine print in a textbook or a newspaper of some sort, it would be considered a simple microscope because of the fact that it only has one lens in it. It's only one lens. When using a magnifying glass, images are going to appear about 3 to 20 times larger than the object's actual size. So that's its magnification. It's going to take that image, and at the very max, it's going to take it up to 20 times larger than its actual size. When we start comparing microscopes, you're going to see that those go even further. So Leeuwenhoek's, for instance, Leeuwenhoek's simple microscope, his particular microscope had a maximum magnifying power of about times 300, which meant that the image, what he was looking at, he could see it 300 times its actual size. So again, much better than an actual magnifying glass, and much better than just the unaided human eye. We're able to see it 300 times its actual size. So because of that, that's why he was able to then find those organisms under there. He was able to see bacteria and protozoa. Whereas your most common type of microscope is going to be called a compound microscope. These are the ones that we have in our laboratories here at ATA, where you'll see them just in most of your labs, in different medical offices as well. A compound microscope is going to contain more than one magnifying lens. So that's what we'll see. There's going to be two, and the combination of the two is going to give us the total magnification, or that magnifying power. So a little bit different than what we saw with Anton van Leeuwenhoek's simple microscope. What we'll also see sometimes, a compound microscope is sometimes referred to as a compound light microscope. Don't be thrown off by that. It's still the same instrument. It's sometimes called that because of the fact that light shines up from underneath so that we can see the image on the slide a little bit better. So because visible light is our source of illumination for that instrument, a compound microscope can sometimes be called a compound light microscope. And talking about the compound microscope's magnification or magnifying power, at max, a compound light microscope will usually magnify objects about 1,000 times their actual size. So much more advanced than Anton van Leeuwenhoek's times 300 simple microscope. Now we're going up to 1,000 times their actual size. So that's what's mentioned here. The resolving power of a compound light microscope is approximate 0.2 micrometers. Remember, the unaided human eye was 0.2 millimeters. So this is 1,000 times better than the resolving power of the unaided human eye. So much, much better here is what we're able to see with a compound microscope. Now, This gets into wavelength, and I don't test you guys to, on wavelength, but it talks about, how this light can be seen. The wavelength of visible light is about 0.45 micrometers, and that limits the size of objects that can be seen. So it also bringing that light in there sometimes can make it, easier, sometimes more difficult. And that gets in, that is also a part of what we're able to see with a compound microscope. Objects cannot be seen if they are smaller than half of the wavelength of visible light. So a lot of viruses, because they're smaller than that wavelength of visible light, we're not going to be able to see them on a compound microscope. So some viruses are a lot smaller than this. We're going to need a more advanced microscope, which we'll talk about towards the end of this chapter, to see those really tiny viruses. Today's laboratory microscope contains, again, remember, a two-lens system. The compound microscope has two, and it's the combination of those two that gives us our total magnification. So the eyepiece, so what we look through at the top, and I'm going to show you a picture of a microscope so you can see what I mean by this. This is referred to as the ocular lens. That by itself is only going to magnify that image 10 times its size. So not even as good as a magnifying glass. If we're just looking at that ocular lens by itself, we're only seeing the image 10 times its actual size. But what happens through a series of, the instrument itself is a marvel and, and inventions, and they were able to come up with mirrors and reflections and able to see a second lens, and the combination of the two will magnify that even more. So we have underneath, we have what's called an objective lens, and that's going to take that image up to 4 times, 10 times, 40 times, and then 100 times the size. So those are your 4 most commonly used objective lenses. So let me show you what happens here. This is your typical compound microscope, and up here at the top, this is your eyepiece. This is what an individual will look through, and you guys hopefully will have a chance when you guys get into your nursing classes. Hopefully you guys will have a chance to look at the microscopes and be able to take a look at something on a slide. What happens is the image is here on the stage. You put a slide on the stage, you can typically lock it into place so it doesn't go anywhere, and then the stage itself will move around if you need to adjust where the image is. But right on top of the stage, you guys see here's the objective lenses. I know on this picture you can only see 3. There's probably another one behind this middle one, and that's your 4th. But you can see it's on a rotator, a rotating device. And what happens is you start on that times 4. So what happens is your eyepiece, which is times 10, and then you're on the smallest objective lens, which is times 4. You're looking at 10 times 4, which is 40. So you're looking at an image 40 times its actual size. So again, not quite super significant, but you're still seeing it a little bit better. And what you do is you bring that into focus and you slowly switch it to the next largest objective lens, and then the next largest, and so on, and bringing it into focus each time. So, but that's what it is. It's the combination of that times 10 eyepiece, and then the number on the objective lens, and then the multiplication of the 2 is how you're going to see that image. So, and this slide here is going to show you exactly what I mean by that. So here's what I meant at the very beginning when I said maybe a little bit of math today, but it's basic math, and an easy way to do this. So your total magnification, again, is calculated by multiplying the magnifying power of the ocular lens by the magnifying power of the objective lens. So as I mentioned, if you're looking through the eyepiece and then you have it on the times 4 objective, you're looking again, 10 times 4 is 40, so your total magnification is 40. When you then switch it to the next largest objective lens, which is times 10, again, you're seeing now 100 times the total magnification. That's the object you're looking at is 100 times its actual size. Then you switch it to the next biggest, which is 40. 10 times 40 is 400. So you can see where I'm going with this. And finally, the last one, the biggest objective lens is times 100. 10 times 100 is 1,000. So that's again where we're seeing that the maximum total magnification for a compound microscope is 1,000 times its actual size. So again, just basic math here. If on a test, if I asked you guys, okay, an individual is looking through a microscope and he or she has it on the times 40 objective lens, What is the total magnification? Easy way to do that, add a 0. Because again, you're multiplying it by 10, which again, essentially just adds a 0. So on the times 40 objective lens is what the question said, add a 0 to that and your total magnification is 400. That's because your eyepiece is always times 10, and that number times 10 just adds a 0. So easy way to do that if you get that on a test, just FYI on that. Okay. Then when images, if you guys have ever looked in a textbook, probably saw some in your anatomy book, probably see some as you're skimming through your microbiology book. If you ever see an image that looks like it's an image straight from a microscope, that happens. We can take pictures with microscopes. Photographs taken through the lens system of the compound light microscope. These are called photomicrographs. Pretty easy to remember because the term photo means picture, and then your micro, again, is what we're looking at, are these microorganisms, and graph, again, a photograph is a picture. So we're looking at a photomicrograph. Okay. Okay, so again, as I mentioned earlier, that a compound microscope can sometimes be called a compound light microscope. Even more so, sometimes people give it a different name. Again, don't be thrown off by this. It's still the same instrument, but sometimes because, again, light is that source of illumination, it gives us a very bright background. So because objects are viewed against a bright background, sometimes individuals call it a bright field microscope. So if you ever see that as a bright field microscope, we're still referring to a compound microscope or a compound light microscope. Again, just talking about again, the background is bright. Sometimes images cannot be seen with such a bright light. So there's a condenser. If a condenser is replaced with what's known as a dark field condenser, then instead the bright background becomes a dark background. So if that happens, the illuminated objects are seen against that dark background, and it's referred to as now a dark field microscope. So it's still a compound microscope, but we're seeing that the background is now dark, so we call it a dark field microscope. There are other types, so in the same sense, these are just more advanced versions of our compound microscope. We're still seeing the same, it's still a very, very similar instrument, but sometimes, again, backgrounds are a little bit different. So these compound microscopes, we have what's called phase contrast microscopes and fluorescence microscopes. They still fall in the compound category, meaning that images are not going to be any bigger than 1,000 times their actual size, but we're seeing, again, just a little bit different. So for instance, this is the dark field image. So I'll show you exactly what I mean with that the background is no longer bright. This particular image would not be able to be seen, this particular bacterium, because of its coloring, because of, what it looks like. So we replace that condenser with that dark field condenser. And here you can see, we can clearly see this bacterium now. Okay. So talking about these, again, advanced compound microscopes, phase contrast microscopes are used to observe unstained living microorganisms. They're easily seen because the light refracted by the living cells is different from light refracted by the surrounding medium. So just a little bit different. I'm going to show you an image on the next slide that shows you some examples of these phase contrast and fluorescence microscope. The difference between again, your compound microscope, your phase contrast, and then what's called a fluorescence. A fluorescence microscope will contain a built-in UV light source. So it's an ultraviolet light source. Again, we think UV, we think sun's rays. Very, 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 very similar. That it's not just your standard light that's being used here. We're looking at an ultraviolet light. So when ultraviolet light strikes certain dyes and pigments, these substances are going to emit a longer wavelength of light, and that causes them to glow against a dark background. So here's an image of a phase contrast. You can see compared to an average just compound microscope image, here's your phase contrast that adds that little bit of, again, that contrast to that image, and you can see it a lot clearer. And then here's what I mean by that fluorescence. Look at how this UV light makes this, almost looks like this image is just glowing and coming out at us a little bit better and a lot clearer. That's where that UV light is going to be really helpful for certain microorganisms to be able to be seen. So that's the difference between those two. And again, they both fall in that compound light microscope. So images are still the same size, as you can see in this comparison picture here. We're still not seeing anything any bigger, but we're able to see it a lot clearer. Okay. Electron microscopes are a little bit different. Electron microscopes, we're going to go a whole lot bigger now, meaning that we're going to be able to amplify that image. That magnifying power is going to be a lot greater here. In an electron microscope, these are going to enable us to see those extremely small microbes. Remember earlier we said in microorganisms that are smaller than the wavelength of visible light, they're not going to be able to be seen on a compound microscope. So here's where the electron microscopes will come in. Your very, very small viruses, such as rabies and smallpox, those are really tiny viruses. They're going to be able to be seen here. Unfortunately, in an electron microscope, living organisms are not going to be able to be viewed. Unfortunately, the procedure itself uses an electron beam, and that procedure kills the organism. So we would unfortunately not be able to see anything living in an electron microscope. And again, as it mentions there, an electron beam is used as that source of illumination instead of just light. This is going to be a little bit more harsh. So electron beam is used and magnets are used to help focus that beam. And that again is going to help aid in that bringing up that magnification a whole lot greater. So electron microscopes have a much higher resolving power than your compound light microscopes. And there are two different types. We're going to see transmission and scanning. And really the big difference between the two, I'm going to have you guys just look at an image of the two. You guys aren't going to have to worry too much about the difference between the two. This just shows you a picture here of someone using a transmission electron microscope. You can see it's a much larger, much more significant instrument. Again, it uses an electron gun to fire a beam of electrons through a very extremely thin specimen. So something, less than 1 micrometer. An image of that specimen is then produced on a phosphor-coated screen. So there, this image is able to come up and, she is going to be able to see that then. Magnification is approximately 1,000 times greater than a compound light microscope. So 1,000 times greater than 1,000 is 100,000 times its actual size. So that tells you how advanced an electron microscope is. So the resolving power, we're going to be able to see things that are 0.2 nanometers. So again, you're very, very tiny viruses. Remember, the average virus was about 10 nanometers to 300 nanometers. So even smaller than that, if we're looking at a really, really small virus, we're going to be able to see it using this transmission electron microscope. And then here you can see the image of the scanning electron microscope. And again, a very large instrument, even addition of computers to be able to see these images. And just to show you guys what we're able to see with this, this is Staph aureus is a bacteria that we're able to see in the process of replication here. It uses what's called binary fission, which is a way of splitting and dividing and becoming more. And you can see that process. You would not be able to see the actual splitting of these cells in a compound microscope, but you can here using this transmission electron microscope. All right, and then here is the same. You're seeing a lot clearer. You can actually see the dimensions here because of the fact that you're using a scanning electron microscope. You're able to see that it's a sphere more so than just where it would show up as just a 2D image on a compound microscope. You can see it a whole lot clearer here. So the big thing to know with those electron microscopes, again, is that it uses the electron beam and magnets to help, again, see the image and focus that electron beam using those magnets. And also know that using an electron microscope, we're able to see up to 1,000, well, I should say 100,000 times the object's actual size. Okay. And guys, that is the end of chapter 2. I just wanted to show you guys in that chapter, so I know that's short and sweet, just how we view the microbial world. Again, using your most common microscope is going to be that compound light microscope or bright field microscope. But just knowing the different things about those compound microscopes, how it can be, we can replace the condenser with the dark field condenser to see it on a dark background. knowing how we can then see with phase contrast and fluorescence microscopes, we can see images a little bit clearer, certain ones even clearer using the UV and using that phase contrast, that particular light that bounces off certain living cells. And then again, the electron microscopes, knowing that they're a little bit more advanced and can see images a whole lot bigger. So just looking at, again, how we view that microbial world. And, and you guys know, we talked last week about Anton van Leeuwenhoek, how he began with just that real simple microscope. And we've just come a long way since then. So who knows where we will go in the future. All right, guys, if you all have any questions, let me know.